Hello and welcome to session 5 of Basic Statistics and Data Interpretation. This is about correlation and linear regression. My name is Emily Isles and I work at the ARC West. The learning objectives for this session are to understand and interpret, as well as understand the differences between correlation coefficients and linear regression coefficients. In the last session with my colleague Lauren, you just learned about risks and odds, which are used with categorical and binary data. Correlation coefficients are used for continuous data, something like height, and linear regression coefficients relate to linear regression, which is a type of regression that deals with continuous outcome data. There are different types of regression for different data types and patterns, but we're focusing on linear regression in this session. We are now going to talk about measuring associations between two continuous variables, such as height and weight. The Pearson's correlation coefficient, often just referred to as the correlation coefficient and indicated by lowercase r, measures the strength of the linear association between two variables. It's important to note that it does only measure linear relationships between two variables, and there could be other relationships between these variables that isn't indicated by r. This could include exponential or step change type relationships or any other sort of relationship that isn't linear. The values of r, or the correlation coefficient, can range from -1 to +1. A positive r indicates that variables tend to have higher or lower values together, whereas a negative r shows that high values of one variable tend to be associated with low values of the other, and a value of 0 shows no linear association between the variables. So remember that this could still have an association, but it might not be a linear one, so it's important to look at the data. And on the following slides, you'll see different values of r and how we might interpret them and how they'll look on a graph. While we're unlikely to find a perfect correlation in practice, this is what one may look like. This is a perfect positive correlation with an r of 1. And you can see that the graph goes up like this in a perfect straight line. An example of a positive relationship would be the one found between height and weight. As you get taller, you tend to get heavier. It's very similar for a perfect negative correlation. You can see it has an r of -1, and this is what the graph looks like, a straight line going down. You can see a negative association perhaps between age and maternal anxiety. So for 0 correlation, so an r of 0, it could mean that there's no correlation or that the association might be there, but it's not linear. The graph on the left shows 1 r equals 0, and you can see you have a pattern that looks a bit like this. And then you have your line of association down the middle. This could be, for example, the height and length of hospital stay post-op, and our second r equals 0. We have the same line through the middle, and it could be, for example, birth weight and some sort of negative health outcome, but you can see it has this shape to it. So I have to emphasize the importance of checking for nonlinear associations between your variables. So graphing out your variables on scatter plots is very useful as an initial thing to do when you're looking at your data. Scatter plot and its correlation coefficient. This scatter plot shows the association between length at birth and weight at birth. As you can see, there's a r value of 0.77, which is close to 1. It's positive, and you can see it's positive on the graph due to its shape, and it corresponds to a reasonably strong positive association between length at birth and birth weight. To sum, correlation coefficients describe the strength of a linear association between two continuous variables. It's completely symmetrical, so in math terms that means the correlation between x and y is the same as that between y and x. To use our example that we had in the previous slide, it means the correlation between height and weight at birth is going to be exactly the same as that between length and height at birth. To put it a bit more simply, it means it doesn't matter which order you analyze the two continuous variables, the correlation will be the same no matter what. So if you do one first and then the other, or the other first and then one, you'll see the same correlation. However, the thing to remember that's quite important is that the correlation coefficient doesn't tell us any more than that there is a linear association and its relative strength. It does not tell us how much the y changes according to a change in x, for example, but that is why we have our regression coefficients, which we'll discuss next. So regression goes farther than correlation and allows us to describe the association between the two variables. Regression allows for a more formal description of the association between two variables, and it's a line described by an equation. You need to know what the exposure, or x, is, and what the outcome is, or y. You need to know the units of the variables when you interpret it. So if you have weight or height, you need to know if that weight is in kilograms or pounds or grams in the case of babies, and for the height you need to know if it's in centimeters or inches or some other measurement. And regression allows us to estimate the value of our outcome per unit change in the exposure. Here we have an annotated version of the same graph with our equation. So we have the equation, which is y equals a plus bx. You may remember this from another course you've been on, a math course or a stats course, or perhaps from school. So let's go through it. We know about y already, which is our outcome, and it's on the y-axis, and we also know about x, which is our exposure, that's on the x-axis here. And then we have two slightly newer things. We have a, which is the intercept on the y-axis, which is when x is equal to 0. And you can see this is where the two axes collide. So this is the origin, which is 0 value for each y and x at this point. And a is the point on the y-axis where the x is equal to 0. So in our case it's here. And then we finally have our regression coefficient, which is represented by b, which is the slope of the line. And you can see b is right here. And it's represented by this little triangle, because other people might also call it the rise of the line. So to calculate b, you divide the vertical side of the triangle by the horizontal side of the triangle, and it's the steepness of the line. So if you had a very high positive value of b, which is sometimes also called beta, you get a line that looks something more like that. And then if you had close to 0 value of b, you'd have a much less steep line that looks something maybe like that. And then if you had a negative value, which is entirely possible, of your regression coefficient, you might get a line that looks something more like that. Looking at this real example, which is a scatter plot showing the association between length at birth and height at age 11, both in centimeters, just looking at the scatter plot, does it look as if there's an association between the variables? Though it does look a bit like a random cloud, and it's not immediately obvious, when you fit a regression line, there does appear to be a positive association between the two. You can see the line just here. So this is the regression equation associated with this line, and you can see that we get an A, or intercept, of 115.5, which isn't actually on the graph just now because the graph has been truncated for legibility, and the axes haven't been continued to 0, but the line would continue until it crosses the y-axis. You also have your beta value, which is here, or your b value, which describes the gradient, slope, or rise. All these terms are used of the line. So you have beta and b. So to interpret the equation, your height at 11, which is your y, so we have height at 11, which is our y and our y-axis, is equal to our a, which is our intercept, which is 115.5 centimeters, which is somewhere over here, plus 0.7, which is our b, or our beta, or our slope, or our gradient, multiplied by our length at birth, which is our x, which is also shown on our x-axis. So you can interpret that as, on average, for each centimeter increase in birth length, height at 11 increases by 0.7 centimeters. So you can put that as, for every centimeter increase in length at birth, we can expect on average a child at 11 years old to be 0.7 centimeters taller. Here is an example how we can use the equation to predict the height at 11 years for various lengths at birth. If a baby is 45 centimeters long at birth, how tall would they be predicted to be at age 11? So we take our equation, which has our height at 11, which is our y, and it's equal to 115.5, which is our a, plus, sorry, that's a very ugly plus our 0.7, which is our b, multiplied by our x, which is birth length. I'll give you a little bit of time to calculate it on your own, but you would put the 45 centimeter in here. Okay, we'll move on to going through the problem. So here you can see the steps for our equation. Y equals a plus bx. So you substitute in 45 as your x, or your birth length, and by order of operations you do the multiplication in the brackets first. So you get a value of 31.5, and then you add them together and you get your predicted height for a child at age 11 who was a baby at 45 centimeters at birth. So that's your y, your predicted y. Just to keep a note, we can't make predictions about a baby who is less than 35 centimeters long at birth or more than 60 centimeters long at birth, because this is outside the range of our data. And since we don't have observed data on babies of those lengths, the relationship may not be linear, so we must be cautious about this. When we're using regression to describe the association between variables, the intercept is of less interest, so often we just present the regression coefficient, since we are interested more in that. As with any estimate, it's important to have a confidence interval around it, because it could be very wide, which would suggest that we should interpret the regression coefficient with caution, because the confidence interval gives us a likely range. You also present a p-value for the estimate. So for our b value of 0.7, we have a 95% confidence interval of 0.5 as our lower bound and 0.95 as our upper bound, and a p-value which is less than 0.001, so we can be pretty confident in our estimate. As mentioned earlier, it's important to control for confounding variables, and regression allows us to do that by including these variables in the model, as well as the exposure and outcome of interest. This is called multivariable analysis. Whether the measure of association is a risk ratio, an odds ratio, or a regression coefficient, it is good practice to present unadjusted or crude and adjusted results, so that you can see how much the adjustment for confounding has changed the result, which in other words or more simple terms is how important were the confounders. We return to our example of birth length and height at 11, both in centimeters. There are several potential confounders. These could include gestational age, parental height, and deprivation, and other possible confounders that you could think of related to birth length. So we have our unadjusted coefficient, which is the one we've been looking at previously, which is 0.70, with a confidence interval between 0.45 and 0.95 and a reasonably low p-value. The adjustment has changed our results, so our adjusted coefficient is 0.59 with a confidence interval of 0.3 to 1.1 with a p-value of 0.016. In our case, this adjustment has decreased the size of the estimated effective birth length on height at 11, so it means that these other confounders have a reasonable influence on our outcome. To sum, linear regression can be used to explore associations when our outcome of interest is continuous, and logistic regression can be used to explore associations when the outcome of interest is binary. For either type of regression, exposure variables can be any type of data, so continuous, something like income for example, binary, something like a yes or no question, and categorical, which could be something like gender or education categories. Other names for regression coefficients, so our B, can include effect size, parameter estimate, and as I said earlier, the beta coefficient. These all mean the same thing and are often field or industry based. So for one final recap, this is the differences between correlation and regression. So correlation measures the strength of a linear association, whereas regression measures the expected change in the outcome per unit change in the exposure. So regression gives you a better idea of what change is happening, whereas correlation coefficients give you an idea of if there is a linear association. So the units for correlation coefficients are unitless, whereas for regression it depends on the outcome and exposure variables. In our example, our units were centimeters. The minimum and maximum values for correlation coefficients are -1 to +1, whereas for regression coefficients they can be at almost any value you can imagine, so it's -∞ to +∞. And for both, there's no difference when the value has no association, so they both are 0 when there's no association between the outcome and the exposure, or the x and the y. Thank you, everyone. That's the end of the basic statistics and data interpretation course. We all hope that you've enjoyed it and found it helpful. Thank you very much.